All right, so let's go ahead and get started. So I think we finished up, we did part A of this problem yesterday. We took f of x was a product, 2x plus 9 times x squared minus 12. You wanted to find an equation of the tangent line at x equals 3. So the ingredients, so to speak, to cook up this tangent line, if you allow me to use a cooking metaphor. Okay, so first of all, you need the derivative. Okay, because the slope of the tangent line at 3 is going to be the derivative evaluated at 3. So we found the derivative using product rule. So what I did was I took the first function, 2x plus 9, times the derivative of the second. The derivative of x squared minus 12 is just 2x. Plus, and then I took the second function, x squared minus 12, and multiplied by the derivative of the first. The derivative of 2x plus 9 was 2. Okay, and then I plugged 3 into that derivative, and we got 84. Okay, so the rate of change of this function at 3 is pretty high. It's changing by 84. You're changing by a value of 84 per unit, okay, with respect to x. And then you plug 3 into the original function. This is going to give you a point on the tangent line. Okay, remember at 3, right? The point on the tangent line is also on the graph of the original function. Okay, I can draw the picture again just to have a visual.
Hey, Chris.
Yeah, what's up?
Could I get a handout from
Yes,
yesterday,
sir.
please?
Yeah, because I think you had to run out, right, before I was able to pass you one.
I think so.
Okay, so you have some function, f of x, and fix an input value, say a. That's gonna, and then you go up to the curve at a, okay, and you obtain a point on the graph. This point has coordinates a, f of a. Right, plugging a into the function gives you the y coordinate. And then you can look at the tangent line, and the slope is f prime of a. Okay. So we plugged a into the derivative to get the slope. A for us was 3. We plugged a into the original function to get the y coordinate of the point on the tangent line. And then from there, I'm just using the point slope formula. I took y minus the y coordinate of a point to get y plus 45. On the right-hand side, I did the slope of the tangent line, 84, times x minus the x coordinate of the point, which is 3. Okay. And I don't care if you put it in point slope form. You can just leave it in slope intercept form. Okay. Or sorry, I don't care if you put it in slope intercept form. You can leave it in point slope form. Did I say it the other way around? Yeah, that was by accident. What I mean is you don't have to put this in the form y equals mx plus b. You can just leave it like this. Okay, that is the equation of the tangent line. Now, I think yesterday, Chloe, you were even asking, like, you were just curious, when do we need to simplify our derivatives and when don't we? On your homework, I did look at the written. The directions do say to simplify your derivatives as much as possible. And as much as that sounds like it's not fun or extra work, you will have to do it later anyways. So I'm just going to keep the directions, simplify your derivatives. It's going to pay off in the long run. Okay. All right, so part B says, does it say find the values of x where the tangent line is, or yeah, find the values of x where the tangent line to the graph of f is horizontal. So find values of x, I'll just write it this way, where the tangent line is horizontal. Okay, and we'll have to do a little bit more of this later as well. In case anybody wants to know where we're going with all this, once we actually have all of our derivative rules, we're going to basically describe the shapes of all functions, the shapes of their graphs, being able to use derivatives. We'll be able to know when they increase, when they decrease. We'll learn about second derivatives. So after you take a first derivative, you can take a derivative again. That'll give you some insight into the shape of the graph. And knowing where tangent lines are horizontal are going to be important as well. Even looking at this graph up here, there's a couple places where the tangent line is horizontal. There's one right here, and there's one right there. Notice where this tangent line is horizontal gives you a local maximum. And the other place where the tangent line is horizontal is where there's a local minimum. Okay, so you can let that go in one ear and out the other for now. Okay, so these are the kind of things that we're going to be talking about later to describe the shapes of graphs. Okay, so that's why we need practice with this now. So find all the places where the tangent line is horizontal. Now, if a line is horizontal, what is its slope going to be? 0, right? Because if something's horizontal, are the outputs really ever changing? No, so the rate of change would be 0. Okay, so what am I going to want to do with my derivative f prime of x if I want to know where the tangent line is horizontal? Yeah, say that out loud, Sergey, so everyone can hear.
Set it equal to 0.
Yeah, you're going to take your derivative, set it equal to 0. That's going to, solving that for x is going to give you the places where the tangent line is horizontal. So we're going to set f prime of x equal to 0 and solve for x. Okay. Now, before I do that, is everybody okay if I erase maybe just this bottom part about the tangent line real quick? Before I do this, now is where maybe simplifying your derivative might pay off. Okay, so I'm actually going to multiply everything out and simplify. 2x times 2x is 4x squared. All I'm doing here is distributing the 2x. And then 2x times 9 is 18x. Plus, over here we'll distribute the 2. I'll get 2 times x squared plus 2 times negative 12, which is minus 24. And when you add like terms, you get 6x squared plus 18x minus 24. Oh, is it locked?
Yeah.
I'll come flip that little switch. So look over my work, make sure that I multiplied everything out correctly.
For this one? You plugged it through into the derivative function.
Yeah, what you missed yesterday, Reese, was if you have a product, the derivative is just first function times derivative of the second, plus, and then you do the second function times derivative of the first.
Okay.
Scott, you need one of these handouts from yesterday?
Yeah.
And Reese, I gave you one?
Yeah.
Okay. Okay. So now that I've simplified my derivative, let's set this equal to 0. So 6x squared plus 18x minus 24 equals 0. And then who remembers well, there's really 3 ways to solve a quadratic equation. So anybody think of them? Okay, so one's factor or FOIL backwards. Okay, so we can try factoring. That's what I'm going to try first. If factoring doesn't work, you can use the quadratic equation or quadratic formula. There's a third way called completing the square, but I think I'll put that off for now. Okay. If we need it at some point, I will remind everybody how to complete the square. Okay, so first of all, is there any constant or coefficient that all 3 of these terms have in common?
6.
Yeah, I think 6 divides 18 and 24. So you can start by factoring out a 6. And I think you'd be left with x squared plus 3x minus 4. Okay. Now, what's one thing I can do to simplify this a little bit? I can make this 6 go away if I just divide by 6 on both sides. Right? But what's 0 divided by anything on the right?
0.
Yeah, still 0. So if you divide both sides by 6, you will get x squared plus 3x minus 4 equals 0. So that 6 out front doesn't really have anything to do with what the solution is. And then I think we can factor this thing. We can split it up as a product of 2 binomials. To get x squared as the first term, these factors have to start with x. And then what's the trick again? You're looking for numbers that multiply to the minus 4 and then add to the 3, and what's going to work for that?
X minus 1.
X
plus 4.
Okay, so minus 1 and plus 4 should work. So that implies or tells us x equals 1 or -4 is where the tangent line is horizontal. And like I said, later we'll talk about what that means graphically. Essentially that just tells you where your peaks and valleys are. Like at 1, maybe it increases to a high point at 1 and then decreases again, and maybe at -4, you're hitting a minimum or something. Okay. But we'll talk about that later. What's another way of thinking of it? It's not necessarily just where the tangent line is horizontal, but what would the rate of change of the function be at those two values?
0.
Yeah, it's 0. Those are the two values of x where the function isn't changing. So if this was a profit function or a revenue function, those would be the two values, or those would be the production levels where, say, your profit isn't changing at all. Okay. All right. Any questions there? Because we're going to move on and tackle the quotient rule, which again is a little bit different. It would be nice if the derivative of a quotient was this derivative of the top over the derivative of the bottom, but unfortunately it doesn't work out that way. So make sure you're really careful. I usually see a student make that mistake at least once on a test. Okay. So we found the equation of a tangent line at a place, and then we also found the two inputs that give us a horizontal tangent line. So now we got to talk about the quotient rule. And this is the second to last derivative rule.
So is T stand for top and bottom?
Yeah. I would have preferred N and D for numerator and denominator, but I will accept this book's abuse of the notation. I think it at least makes it more accessible to everybody instead of being super. That's one thing I like about this book is there's times where it breaks from being super formal, kind of phrases things in more layman's terms. Okay. So yeah, they're going to use T and B for top and bottom. So if your function f of x is a fraction or a quotient of functions, it can be written as T of x over B of x. Okay, and then yeah, for top and bottom. Just like for product rule, it was f and s for first function and second function. I think it just helps you remember the rules a little bit better. Now again, I'm not gonna prove this. Anybody in here is welcome to come to my office and say, why is the product rule what it is, or why is the quotient rule what it is? Okay, but I don't think for a business calculus class that it's appropriate to do those derivations in class. Okay. So if the derivatives of t and b exist, the derivative f prime of x is going to also be a quotient. You start with the bottom function first in the numerator. So whatever is in the bottom, you start with that on top. Multiply it by the derivative of the numerator, the top function. And then here's what's a little bit different, right? The product rule would have a plus here. The quotient rule has a minus. And then it's the other way around. The top function times the derivative of the bottom function, all over the bottom function squared. Some of you might like this. Let me see if I can think of how to say this. Low d high minus high d low over low squared. I don't know where this comes from. Every single campus I've ever been on and sat in when I sit in the tutor rooms. Some people remember the quotient rule as low d high minus high d low over low squared. So low just represents the bottom function. D high is derivative of the top. Minus high, that's the top function, times the derivative of the bottom over the bottom squared. So if you like mnemonics, if it helps, great. Go ahead and think of that when you're thinking of what the quotient rule ought to be. low d high minus high d low over low squared. Okay. In fact, if I check the textbook, they might even have it in there somewhere as well. But one thing I don't like is that this is blurry sometimes. There, that's a little bit better. Okay. So let's do some examples here. Now again, be careful. The derivative of a quotient or a fraction, it's not just derivative of the top over derivative of the bottom. Okay, be very careful. Same is true of a product. The derivative of a product is not just the derivative of the first times the derivative of the second. What I would make sure you do is just write this rule down as many times as you need. Someone might need to write this down once to get it. Someone else might need to write it down 10 times. Okay? So maybe I'll stop and talk about that for just a second. Okay, so my strategy or my experience in math is anytime there's a theorem or a definition, anything that you have to use to solve problems, I would go up to a whiteboard or I'd get out some paper and I would write them down over and over and over till I wanted to almost just kill myself because I was so bored. Okay, it's not fun. Practicing is not always fun. But that's what you got to do if you want to do well. Okay, and I would kind of do a mixture. I'd write down all the definitions and theorems over and over, and then I would go do as many problems as I could over and over and over. And then if I had a question or I didn't get something, I would make sure I either went to my instructor or went to a tutor. I'd always make sure I got my questions answered. Okay, so that was just my strategy that always worked for math. And other people might be different. Instead of just writing stuff on the board, maybe you're a flashcard or a no-card person. Okay. Point is, though, you have to dig in and work and figure out what works for you. Okay. So sorry about my little lecture spiel there. So example 3, we're going to differentiate some quotients. So part A, we're going to find the derivative f prime of x if f of x is the quotient minus 4x cubed plus 2x over 3x. And Amanda already pointed something out. Some of these power functions could be with square roots too. But what do you always do if you have a radical or a square root? You always rewrite it with, the fractional exponent form. Okay. All right. So we're going to do f prime of x by a root. It's again going to be a quotient. Now, what do I start with in the numerator? Based on our formula on the left. Okay, it's going to be the bottom function, b of x, which is for us 3. Okay. And then I multiply that now by what?
The derivative of the top.
Okay, the derivative of the top, which is going to be minus 12x squared plus 2. I might run out of room here. Okay. So I did the bottom function times derivative of the top. What's the sign in the middle in the numerator? Make sure you always put a minus sign. And then now you just do it the other way around. You'll do the top function times the derivative of the bottom. The derivative of 3x is just positive 3. And then you divide everything by your bottom function squared, so you'll have a 3x squared down here. And then what would you have to do if you wanted to simplify this out fully?
You'd have to FOIL.
Reverse FOIL, right? You're right. So essentially FOIL, which in the case where the one term, if it's just a single term, that's just distribute. So you're going to distribute the 3x and the 3. It's the same idea as FOIL. Okay. Since we have to do it on the homework, we'll go ahead and do it anyways. Okay, so we'll distribute the 3x through. That'll give me a minus 36 x to what power?
Cube.
Yeah, x and x squared give you a cubed. 3x times 2 is plus 6x. And then I have to do minus, well, let's do a couple things. I'll distribute the 3, and then the minus gets distributed. It changes this to a plus and this to a minus. So 3 times 4x cubed, and then the signs change. It's going to be a plus 12x cubed. 3 times 2x is 6x, but multiplied by a negative will give us minus 6x. And then the denominator, when you have a product to a power, remember you have to square the 3 and the x to get 9x squared. And then do we get some nice cancellation?
Yeah, the sixes go there.
Those go away. And then 12x cubed minus 36x cubed is minus 24x cubed over 9x squared. Wow, this one actually simplifies quite a bit.
Yeah.
And then let's see, is there something that goes into 24 and 9?
3.
I think 3 will. I think you'll get minus 8 thirds. 3 goes into 24 8 times. 3 goes into 3 3 times. And then x cubed over x squared is just x. And sorry, yeah, about the... Can you still see it, Kennedy?
Yeah.
Okay. So actually it just becomes minus 8 thirds x. Okay. Now, did I have to use quotient rule on this function? What do you think?
Yeah.
Is there any way this could have been simplified first?
Could have rewritten 3x as 3 to the, or 3x to the negative 1.
We're taking the next out.
Yeah. So, yeah, there's a couple ways. You could factor out an x and get rid of the x in the bottom, and then you could divide 3 into both terms. You could do what someone else said, and 3 times x is the same as 3 to the negative 1, x to the negative 1. But what I would do is, if your denominator is a single term and the numerator has more than one term, I would just do the split up fractions method. Okay, so what I would do, and everything everybody mentioned is equivalent, but I would rewrite f of x as minus 4x cubed over 3x plus 2x over 3x. This becomes minus 4 thirds x squared plus 2x over 3x just becomes 2 thirds when you simplify the x's. Okay. The only reason I'm doing this is I'm just trying to show you that there are times where you really don't need to use the quotient rule. Okay. If you can simplify, you might be able to just simplify it into an easier form, because now the derivative is just going to be term by term, and you can use the power rule. This 2 is going to come out front to give you minus 8 thirds x, and the derivative of the constant 2 thirds is 0, and that's the same thing we got when we simplified after using quotient rule. In which way it was a lot easier to take a derivative? Yeah, by simplifying first. Now, where you have to be careful, let me see if one of these will do it. Yeah, okay. So now the next one, there won't be any way of getting around using the quotient rule. Not yet, until we have the next section. There's only one more derivative rule yet left, and that's how do you take derivatives of compositions of functions. Everybody in here remember compositions, like f of g of x? Okay. So that's going to be our last derivative rule. Okay, so part B. Is it okay if I erase this stuff? Okay, that was just the simplify first by splitting up fractions, then take the derivative, as opposed to leaving it as a quotient and using the quotient rule. The other good news is that after these sections, you'll be able to take derivatives however the heck you want to. Okay. But I have to make sure we all know the rules first. Okay, part B, this time is y is going to actually be a function of t, so t is the independent variable. We don't see a lot of t's, right, because this is mostly business calculus. All of our business functions usually involve x, where x is the production level. Most of the time, t's don't come in unless you're like in physics and you're doing things that are functions of time. Actually, I lied, didn't I? We did have a problem where we gave the sales in terms of the number of months. Okay, so we actually have seen a business model that uses t as the independent variable. But usually t represents time. Okay, so we're going to find y prime. Now, unfortunately, this one cannot be simplified. Right? The denominator is not just a single term. That can be, so you can't split this fraction up in any way that would be helpful. So we're stuck with the quotient rule. So y prime, and help me out again. What do you always want to start with in the numerator?
Bottom.
Okay, always start with the bottom function. Since you're going to multiply it by a derivative, make sure you introduce parentheses around the t cubed plus 1. And then you multiply it by the derivative of the top. The derivative of t squared minus 1 is?
2t.
That'll be just 2t. So it's the derivative of the first term is 2t, and the derivative of the second term is...
T
Yeah,
on
the
top
T, so it's
instead of 1.
Yeah.
Yeah. So T.
Oh, okay. That's me not knowing how to read, so... Okay, so it should be 2t minus 1. Okay, sorry, my bad. I apologize. Gotta be careful. I think it's just that my eyes are getting bad. That's not good. Getting old kind of... I'm not that old, but getting older sucks, I guess, in certain ways. Other ways, it's nice. Okay, and then what's the sign? We're not done yet.
Minus.
Now we do a minus. And do we just do it the other way around? So we do the top function, and then multiply by the derivative of the bottom. And what's the derivative of the t cubed plus 1?
3T squared.
That'll be a 3t squared. And then I just divide by the bottom function raised to what power?
Squared.
Well, squared. Okay. Well, let's see, is there really... So unfortunately with this one, there's really no nice way to simplify it again other than to just multiply everything out and see if there's a way to cancel off anything in the bottom, but let me see. Yeah, I don't think there's going to be a nice way to simplify this one.
There's not.
Nope. You just have to multiply the whole numerator out. I think I'm going to pass on that, okay? All right, everybody in here, can everybody FOIL? And over here you just distribute, and then distribute the negative, collect like terms, and then see if, it might be the case that you can cancel off with one of the t cubed plus 1s in the bottom, but I'm not sure. Again, eventually what we're going to be doing is we're going to be finding where derivatives are 0, so we'd have to, or where they're undefined. So later on, we'll have to set the numerator equal to 0 and solve, and set the denominator equal to 0 and solve. But for now, we don't really have to mess with that. Go ahead and do part C. See what you come up with.
It's ugly.
Huh?
I said it's ugly.
Is it ugly?
Yeah.
Okay. Yeah, you certainly, in that one, when you have a mixture of powers of x and exponentials,
This is as far as I
the
got.
simplifying part is not fun. But don't simplify it, just write down what the derivative is. And then let me remind everybody of one of the rules. So remember, if you take the derivative of an exponential, the derivative with respect to x of b to the x is always natural log of the base times the original function. So you'll need that when you take the derivative of the denominator. This time I did say d over dx, huh? So somebody help me out. What am I going to want in the numerator? Okay, so start with the bottom function. Make sure you throw in the parentheses. And then we multiply by
4x cubed.
the 4x cubed. That's the derivative of the top. Okay, and then what?
Minus.
Then we'll subtract. And we'll start with the top function. And then multiply by the derivative of the bottom function. Okay, now this is why I wrote this up here. The derivative of 2 to the x would be natural log of 2 times 2 to the x. So I get an ln 2 times 2 to the x minus the derivative of x squared, which is 2x. And then we divide everything by bottom squared. Okay, and yeah, I don't want to simplify that either. Okay, when we get into the graphing functions, you're not really going to get something that's got a mixture of exponentials and powers of x. Okay, it'll either be strictly exponential or strictly powers of x. Okay. So, and this is what I'll say on the test too. I'll say, find the derivatives of the following using product or quotient rule, and I'll say, do not simplify. You can just apply the quotient rule and leave your answer like that. Okay. Alright. So, we'll get to a business economics example now. And then if we have some extra time, I'll just make up a couple on the board and we'll do some extra practice. Is everybody okay? I'm not going too fast? Okay. Make sure my computer's still alive. Okay. Alright, so price demand. Okay, so we've seen price demand functions hopefully on the homework by now, except for none of them were given by quotients. So the number of X DVDs people are willing to buy per week is given in terms of the price in dollars. So the number of DVDs demanded is a function of the price, and it's 20 over 0.1p plus 1. Okay, and I think this agrees with your typical supply demand, right? If the price increases, it makes the denominator bigger, making the whole fraction smaller. And that whole fraction gives us number of units demanded. So this is a function where as the price increases, okay, the number of units demanded will also decrease. Or not also decrease, but as price increases, demand will decrease. Okay, so part A says find the derivative of the quantity with respect to the price. So you're treating P as the independent variable and X as the dependent variable. Okay, now this is again a quotient, right? So how's the formula go again? You start with the bottom function times the derivative of the top.
Which is 0.
The derivative of a constant is 0. Okay. And then minus the top function times the derivative of the bottom function. Yep, so the derivative of 0.1p is just 0.1 and the derivative of positive 1 is 0. And then we divide by
The bottom square.
Yep, just divide by the bottom squared, thank you. And let's see, the first term becomes 0, and then negative 20 times 0.1 is going to just be positive 2, I believe. Someone check that for me in the calculator. I guess you could do 10 times 0.1, which is 1, times 2.
It is 2.
Okay.
Yeah, you're good.
Usually I'm pretty good with my arithmetic, but I do make mistakes.
So we shouldn't boil that out, just leave it like that.
Shouldn't do what?
Shouldn't boil it out.
No, I would just in general leave it as the 0.1p plus 1 squared.
Alright.
Okay. in general, I would only simplify if you need to. Like if you're actually going to do something with this derivative. So yeah, I'll just leave it like this. Now what this is doing is it's giving me the rate of change in units demanded in terms of the price. Okay. So let's answer a couple questions. I don't think these are really any different than they were before. The only new part here was just taking the derivative of a quotient. So part B says, find the demand and instantaneous rate of change in demand when the price per DVD is 20. So we're going to take for the first part, the demand is going to be x of 20. So what's the demand x when the price is $20? And that's going to be 20 over 0.1 times 20 plus 1. And I think you just get, it'll be 20/3.
Yep.
Someone get me an approximation to 2 decimal places?
6.67.
Well, let's do it this way. 6.67 DVDs per dollar. One way to help you with the rate of change is actually, that's why this dx dp is useful. Because the units in the top, x is the number of DVDs, and in the price, change in price, the units there would just be dollars.
Wouldn't this be the total demand though, since we're going from the parent function?
Oh,
Just
oops.
the 20?
Chris, I was testing you. So actually, I should just say DVDs, right? Now, does that really make sense?
No, I've rounded up.
Yeah, let's actually do this. Let's round it up to 7 DVDs. Okay. So it's really what, 6.67, right? Okay, but since this is supposed to be the number of DVDs demanded at a price of $20, yeah, good idea, Ollie. Let's round it up to the next whole number. Okay. So approximately 7 DVDs are demanded when the price is $20.
Hey Chris,
Yeah.
why are you plugging it into like the original equation, not the derivative?
So this is a twofold question. It says find the demand and the instantaneous rate of change.
Oh, okay.
It's okay. I misread a question in my pre-cal 2 class this morning, so it happens to me too. Okay, so that was just the demand part. And I'm guessing this is just a particular DVD, right? This retail chain probably sells a bunch of them. Maybe this is just one particular movie or something.
Yeah.
So yeah, when the price is $20, they can expect to sell about 7 DVDs per week. If you go back and read the original question, it says X is the number of DVDs that people are willing to buy per week. Okay, so if the price is $20, they can sell 7 DVDs approximately per week. Okay, now you want the rate of change in demand with respect to price when the price is $20. So remember, that's another way to denote the derivative evaluated at 20, is you just put the bar down there and put a p equals 20 on the bottom right of that bar. So that means the rate of change when the price is 20. And now I'll plug 20 into my derivative function. Negative 2 over 0.1 times 20 plus 1 squared. Anybody have a...
Negative 0.2 repeated?
So you get, we'll say, negative 0.2 DVDs per dollar. Which really just means that you'd actually have to increase the price by $5. Right? This kind of, to me, it doesn't really make a whole lot of sense, because how can, I guess this would be the rate that the demand is changing when the price is $20. Okay, but to make this actually make any sense, multiply this by 5. That would tell you that you're selling 1 less DVD per week if the price was increased by $5. Okay. So if the price were increased by $5, I guess we can say the retail chain would sell one less DVD per week. Okay. I'm just using that rate of change to make it more sense, so that it makes more sense. Okay. Doesn't really make any sense to sell 0.2 less DVDs. So that just says every time you increase the price by $1, you decrease the number of DVDs by 0.2, meaning if you increase the price by $5, they'll sell one less DVD per week. The question didn't ask for that interpretation, but I thought it was important just to maybe write that down. Okay, and then finally, marginal analysis time. Approximations using derivatives. Now, again, I don't really like this question, or like some of these questions, because they won't really make a whole lot of sense when your quantities have to be given in whole number terms. Okay, but if we want to estimate the demand if prices increase to $21. So remember this whole thing about if you want the demand at 21, it's approximately the previous demand plus, and then what do I add to it to get the approximate? The derivative at 20. So add your rate of change. Right? This is how much it's changing when the price is 20. So we'll take the original quantity plus how much it changes. And that should give us an approximate for the demand at when the price is $21. Okay, so this is going to equal, we already found x of 20 was 7 plus negative 0.2.
So if we didn't round up, it would go down to 6.4 or something?
Yeah.
So then would we round down to 6?
Well, I suppose, shouldn't we really be, yeah, that's a good point, Ollie. Let's use the exact values. Let's use 20/3 plus the negative 0.2. So that was the exact demand at 20. This is the exact rate of change at 20. When you add them together, it gives you an approximate for units demanded when the price is 21. And then what do you get when you plug that in your calculator?
6.44.
So this is 6.44. We'll just say that's approximately 6 DVDs. Okay. So yeah, that's a good point. So there's kind of some limitations with this. Okay, you have to be really careful. All right, it doesn't really make sense to sell 6.44 DVDs. Okay, so in that case, you just have to round to the nearest whole number. But that was a good point Ollie made. I shouldn't use my approximation of x of 20. I should leave it exact and add the exact rate of change and then approximate that result. Anybody heard that general rule of thumb before? Is when you're calculating a value, when do you do your rounding?
At the end.
Yeah, at the very end. Okay. We got 5 minutes left. Anybody have a question about part C? Yeah.
If it was like 6.73, we would still round down to 6 DVDs, right? Because you can't have.
I would just round to the nearest whole number.
Okay.
So follow your general rounding. If the digit after the decimal is less than 5, you round down. If it's 5 or bigger, you round up.
Okay.
Those are just general rounding rules.
But I know, like in past math classes, they're like, oh, well, you can't have half, so round to the nearest like one that like you did sell. Like you can't sell half a DVD.
Yep.
So you sold at least 6.
Oh, I see what you're saying when you're talking about. I see.
Just because we're talking about like DVDs.
So even in this case, when it's 20/3 and it's like 6.66 or whatever it is, maybe I should have still rounded down to 6. Let me think about that. I'll try and make that more clear next time. Okay. So hold on to that question until next time. Let me give everybody one to try. Or do you just want to go home?
Go home.
You want to try one? How about I'll write one on the board, you can write it down, practice it at home. We'll do a couple warm-up questions tomorrow before we start the next section. So I'll give you two. So 1 and 2, find f prime of x if f of x equals, I don't know, let's do 3 squareds of x plus 2x to the minus 2 times 1 over x plus 4x. So there's a product rule one. And actually use the product rule too, don't just multiply it out. And then let's find d over dx of, actually let's switch it to w. We're going to mess around with different letters. D over dw, so derivative with respect to w of 3 to the x, 3 times 3 to the x plus w, sorry. 3 times 3 to the w plus 2w to the minus 2 over w squared plus 4w. So there's a product rule and quotient rule. Get as much of them as you can done, and then we'll do them as warm-ups tomorrow. And then we'll start talking about the chain rule, which is derivatives of compositions. And then, yeah, I'll look into that approximation question. My guess is when you're doing the online homework, you'll probably figure it out. Like if you try to round something up and it doesn't work. So we'll see what happens.
Sorry, what?
All right, see everyone tomorrow.